Okay, welcome back. This is 5.4. There's pen issues. So now we're actually going to dispense with all the limit baloney that we've been dealing with and use this special factoid, the fundamental theorem of calculus. We use this. There's two fundamental theorems. One will kind of connect the derivative and the integral. The other one is going to allow us to evaluate these definite integrals without having to do this limit nonsense. Okay, so first, fundamental theorem of calculus in this book. If f is continuous on some closed interval, and f is big F is the antiderivative of little f on this closed interval, then we can figure out the definite integral of f of x dx by just evaluating the antiderivative at the limits of the integral, believe it or not. So the proof is really quite interesting. So I'll go through the proof of this. I'll try to hit the proofs. You can always fast forward through the proofs if you don't like them. So let delta be a partition of our interval from A to B. And so let's name this, let's make this definition, this partition explicit. So A is x sub 0, then x sub 1, then x sub 2, and then dot, 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 and then x sub n minus 1, and then x sub n, which equals b. Okay. Note from this point, what is f of b minus f of a? We can rewrite that. F of b minus f of a. We can rewrite this in a clever sort of way. We can rewrite it as f of b minus f of x sub n minus 1 plus f of x sub n minus 1 minus f of x sub n minus 2. Okay. And so these would cancel out, and then these next two are going to cancel out. So, plus f of x sub n minus 2 minus f of x sub n minus 3. And then you keep on going, blah, 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 all the way to the other endpoint, f of a. So you would have f of x sub 2 minus f of x sub 1 plus f of x sub 1 minus f of x sub 0, which is, the last one is f of a. Of course, this is f of a. And if you look backwards, these all cancel out in this clever little way of writing the sum. Okay, so let's put this in summation notation, and then we're going to turn it into kind of a Riemann sum issue, and then we'll be able to connect the dots between this stuff and this formula here. Okay, so I'm going from apparently I equals, I want to get the indices right, 1 to n of f of x sub I minus f of x sub I minus 1. Okay, because this function is conforming to all these criteria, this continuity, and there's some differentiability in here. We know that this thing, this function big F of x must work with the mean value theorem. We can apply the mean value theorem here. So in particular, then, by the mean value theorem, there exists a c sub I in each one of these, there exists a c sub I in each one of these intervals such that big F prime of C sub I will equal big F of x sub I minus big F of x sub I minus 1 all over x sub I minus x sub I minus 1. Okay, then we go back to this Riemann sum here, and we're going to kind of rewrite it using this. So I note then this thing back here, this sum of f of x sub I minus big F of x sub I minus 1 is equal to the sum of big F of x sub I minus big F of x sub I minus 1 all over x sub I minus x sub I minus 1 times, sorry, sort of went off the page, times x sub I minus x sub I minus 1. And what's happening is you're kind of getting this Riemann sum looking object, right? So this is equal to, and I can replace it now with this thing, it's equal to the sum of f prime of c sub I times change in x sub I from I equals 1 to n. Okay, so if we take then the limit of both sides of what we have, so what do we have right now? We have from this construction, we have that the sum of I equals 1 to n of f prime of c sub I delta x sub I equals f of b minus f of a. We could take the limit of both sides of this thing over here. This is just a constant, so the limit of constant would just be the f of b minus f of a. But over here you have the limit of this Riemann sum, okay, which, assuming that limit exists, you have the definite integral of f of x. Hence, taking limits, you have the integral from a to b of f of x dx equaling f of b minus f of a. And again, I went off the page. So that's the spiel there. Let's now apply it. All right, so let's apply the fundamental theorem of calculus to this material. And you'll find it quite easy, especially if you've been doing a lot of these Riemann sums in the homework. You're going to be like, oh my God, why did I even bother? Right? So 7 minus 3t dt. So all we need to do is find the antiderivative of this, and then input this and subtract the same thing inputted with this. So this is how we write it. Please do not get creative on me. This is 7t minus 3t squared over 2, and we evaluate it from -1 to 2. Okay. So I take this thing and I plug in 2, and then I subtract away this thing evaluated at -1. Okay, so this thing evaluated at 2, 7 times 2 minus 3 times 2 squared is 4, all over 2, minus, and then plug -1 into this thing. So it would be -7 minus -1 squared is 1, so minus 3/2. Okay, so I have 14 minus 6 minus -14/2 minus 3/2 is -17/2. 14 minus 6 is 8 minus, well, that'll become plus 17/2. So 16/2 plus 17/2 is 33/2. Okay, so a lot easier than before, right? Let's do a couple more here, and then we'll start building towards the second fundamental theorem of calculus. There's a couple things we need to deal with on the way, though. Okay, so number 16, we have the integral from 1 to 8 of the square root of 2 over x dx. And so I need the antiderivative. So this is all 5.1 stuff, really, in the beginning. I'm going to rewrite this as the integral of root 2 over root x times dx. And then you can factor out the root 2. It's just a constant, so root 2 times the integral of 1 all over root x. dx. And I want to integrate using the power rule, hopefully, so I rewrite 1 over root x as x to the negative 1/2. Okay, then I want to find its antiderivative, so I have root 2 times x to the negative 1/2 plus 1 is 1/2. Divided by 1/2 is the same as multiplying by 2. And I need to evaluate from 1 to 8. Okay, so I plug 8 in first, so I have 2 root 2 times the square root of 8 minus 2 root 2 times the square root of 1, which is just 1. Okay. So square root of 8 is 2 root 2. 2 root 2 times 2 root 2 is 8. So I get 8 minus 2 root 2, and that is it. So I get 23. So the integral from 5 to 0 of the absolute value of 2x minus 5 dx. Okay. This is really the integral of a piecewise function. It has two parts to it, so we're going to have to split the integral. The absolute value of 2x minus 5 is negative 2x minus 5, so negative 2x plus 5, when 2x minus 5 is less than 0. In other words, when x is less than 5/2. And then it's positive 2x minus 5 when 2x minus 5 is greater than or equal to 0. In other words, when x is greater than or equal to 5/2. Okay. So we can split this integral then into the integral from 0 to 5/2 of negative 2x plus 5 dx. And then plus the integral from 5/2 to 5 of 2x minus 5 dx. So let's figure that out. This first integral then, the antiderivative, negative 2x squared over 2, so negative x squared, and then plus 5x, and I need to evaluate from 0 to 5/2, plus this other integral, so 2x squared over 2 is just x squared, minus 5x from 5/2 to 5. And then I'm plugging these limits into the antiderivative, so 5/2 squared is negative 25/4, plus 5 times 5/2 is 25/2, minus, plugging in 0 for both of these, you just get 0 plus 0. And then plus, now I have to evaluate this thing at these guys. So I'll have 25 minus 25, and then minus, plug 5/2 into here, 25/4 minus 25/2. Right. So going at it then, on a common denominator here, this will be 50/4. So 50/4 minus 25/4 is 25/4. These are 0, this is 0, and then minus, this will be 50/4. 25/4 minus 50/4 is minus 25/4, but it'll be positive, so plus 25/4. So that'll be 50/4, which will be 25/2. Okay. Okay. We have kind of a mean value theorem for integrals, just like we have the mean value theorem for functions. Let's go ahead and take a look at that thing. So mean, every once in a while it'll come up in proofs, value theorem for integrals. And what does it say? If f is continuous on the closed interval, there exists a number c in a to the b such that the following is true. So basically, the way I remember, f of c equals 1 all over b minus a with the integral up top here. So the integral from a to b of f of x dx. So you kind of think of this numerator as a slopey kind of thing, and same for the denominator. And you know, if you think about the mean value theorem, what did that thing say? That was kind of like f prime of c equals f of x, f of b minus f of a. Right? So as you go from here to here, it's like you're taking derivative. So if you take the derivative of an integral, you kind of get back to where you started. So that's just how I think of it in my head. You know, I'll take my word for it. You know, proving this thing. So, you know, there are requirements for the proof. F has to be continuous. So if F is continuous on the interval from A to B, then there exists the C value such that this thing holds, and it's just basically just the mean value theorem, sort of. Anyways, let's take a look at the proof. So if F is constant, then the integral from A to B of f of x dx is just going to be the integral of some constant dx, which will be k times x integrated from A to B, which will be k times b, plugging b into there, minus k times a, which will equal k times b minus a. In other words, k will equal the integral from a to b of f of x dx all over b minus a. And this will be true for any x in the interval from a to b. So you can say any value, any x in the interval from a to b, this thing will work. Okay? So we presume that maybe f is not constant. Okay? Okay, so suppose then f of x is not constant. Well, we have that f of x is continuous on this closed interval, so by the extreme value theorem, we must have the following. By the extreme value theorem, there must be these points in the interval such that f of this point in the interval will be less than or equal to f of x, which will be less than or equal to this other point in the interval. So there's a max and a min. Okay, there's an identifiable max, which would be this guy, and then there's an identifiable min, which would be this guy. Then you can kind of take the integral of all three sides. Okay, so hence, at that point, you take the integral from a to b of this min value, which would be less than or equal to the integral from a to b of f of x dx, which would be less than or equal to the integral of f of m dx from a to b. These two guys are constants again, right? So we know how to deal with those. That'll just be f of m, in this case, k times b minus a, which would be less than or equal to the integral from a to b of f of x dx, which would be less than or equal to f of big M times b minus a. And then you could divide through by b minus a, and you have f of little m, I should write that cursive, less than or equal to the integral from a to b of f of x dx all over b minus a, which is less than or equal to f of big M. Okay. And then by the intermediate value theorem, there must exist a c in between these 2 points such that f of c is equal to this number. That was from 2.4, the intermediate value theorem. So from 2.4, there must exist a c value such that f of c is equal to the integral from a to b of f of x dx all over b minus a. Okay, so essentially, if you have a curve that's going from f of little m to f of big M, and there's some known point in between the two, as you go from one to the other, it has to cross through that point. Okay. Alrighty then. So that's pretty much it. They'll also note that they consider this the average value of the function. So this object here, they're going to call the average value of f, assuming that f of x is continuous. Okay, in the book, they're going to have problems similar to what we did with the mean value theorem, where you're finding the sort of c value that makes that is the result of this mean value theorem for integrals. Let's look at 51. They want you to find the c value guaranteed by the mean value theorem for integrals. So we have f of x equals 5 minus 1 over x on the interval from 1 to 4. Okay. So we're looking for this c value such that the integral of f of x from 1 to 4 all over, this thing is equal to the integral of f of x from 1 over 4 all over 4 minus 1, which is 3. So I got to find the c value. So I say 5 minus 1 over c is equal to, all right, so I need to evaluate this integral. So I have 5x minus the ln of the absolute value of x from 1 to 4 all over 3. So I have, I'm going to multiply both sides by 3. So 15 minus 3 over c equals, if I plug in 4, I have 20 minus ln of 4 minus 5 minus ln of 1. Okay, so I have 15 minus 3 over c equals 20 minus 5 is 15 minus ln of 4. ln of 1 is 0. So I'm going to move the 15 over. I get negative 3 over c equals negative ln 4. Sort of cross multiply, and so c will equal 3 all over ln 4. Please note that we needed continuity for this to work on the interval from 1 to 4, and certainly this function is. It's only discontinuous at 0. And so those kind of problems. Now we hit the second fundamental theorem of calculus, and we can apply these rules that we just, the mean value theorem for integrals here to prove the second fundamental theorem of calculus. Let's look at the thing first. So section 4, the second FTC. Okay. So note the integral as a function. So basically number 80, now we're thinking of this integral as a function of x, where we're going from 0 to x of some t times t squared plus 1 dt. And if we evaluate this thing, let's take a look at what we get. T cubed plus t dt, which will be t to the 4th over 4 plus t squared over 2, evaluated from 0 to x. And if we put that into here, we'll get x to the 4th over 4 plus x squared over 2. Okay, so what? Well, if I take the derivative of this thing, I get this. Okay, so it's sort of giving you the perfect inverse formula for the integral. Okay, so before we kind of said, you can integrate the thing, but it's not going to give you the exact antiderivative. It's like an antiderivative plus a constant, But here it is in fact, take the derivative of this thing with respect to x, and what do you get? Well, you get 4x cubed over 4 plus 2x all over 2, which is x cubed plus x, which is this thing right here that we were trying to find the antiderivative of. Okay, so that's what we have. So theorem 5.11 then gives us this fundamental theorem of calculus, the second fundamental theorem of calculus. And it's saying that the derivative with respect to x of the integral from a to x of f of t dt is going to get you right back to the f of x, right, where you sort of started. In other words, in this case, the integral and the derivative are kind of pure inverses of each other. Okay. Okay, so let's take a look at the proof of this thing and see how that goes. So we'll define then this antiderivative function as an integral from a to x of f of t dt. We have probably some criteria involved here, so this will hold. Let's look at 5.4 for the second fundamental theorem of calculus. I see a cat. Yeah, so f needs to be continuous on the open interval I. So please define f of x equals this, and suppose f of x is continuous on some open interval I containing a. Then for every x in that interval, this holds. So f of x holds for every x in I. Okay, right. So by the definition of derivative, we go back to our quotient sort of form, difference quotient form for derivatives. We can write f prime of x equals, we can write f prime of x equals the limit as change in x goes to 0 of big F of x plus change in x minus big F of x all over change in x. My only question in the back of my mind is whether or not big F of x is considered to be differentiable. Right. I don't know, maybe because of this definition you're supposing f of t has this as an antiderivative, so therefore this must be differentiable because its derivative is sitting right there or some baloney like that. I don't know, I'll have to go back and look. But anyways, here's the derivative definition. So big F of x equals this thing, and then we could use our definition in place here. So we end up with the limit as change in x goes to 0 of the integral from a to x plus change in x of f of t dt minus the integral of a to x of f of t dt. So I'm just replacing the x portion of this definition with x plus change in x. And then this is just the exact original issue that we're, okay, so then the limit of change in x goes to 0 of this thing. Then x plus change in x from a to x plus change in x is really the integral from a to x, and then the integral from x to change in x. So this difference becomes the integral from x to change in x, or rather x to x plus change in x of f of t dt all over change in x. And then we can use probably like the mean value theorem for integrals from here. So from the mean value theorem for integrals, there exists some c sub I in the interval from x to x plus change in x. So we'll just say c in the interval from, what the heck did I say, x to x plus change in x. And this should be a closed interval, such that we can say that this limit as change in x goes to 0 of this thing is equal to the limit of f of c times this thing right here is f of c. This whole thing is f of c. So this thing right here, yeah, that's it, really. It's just the limit of f of c by the mean value theorem for integrals. And then the limit as change in x goes to 0 of a constant is pretty much just well, we have to consider the c is smack dab in this interval. So as change in x goes to 0, this is pushing the c value to x. So this will actually end up being f of x. Ugh. Okay, so that's not the... I had some issues there doing that proof. Sorry about that. My big issue is just wondering if this big f of x function, this thing right here, is actually going to be differentiable. So I think it's clear that if f is continuous, we could say it has an antiderivative. So big F, it's continuous, therefore it's integrable, therefore it has an antiderivative. So if it's antiderivative would be big F of x, that sort of implies that this thing is differentiable, because otherwise how would I say that if it has an antiderivative, then clearly it has a derivative. You can always, I don't know. Frick, I give up. Anyway, let's look at what the book has and go from there, I guess. There's a whole bunch of questions now in here. So you get the basic kind of fundamental theorem of calculus questions. Big F of x. Figure out what that is. I'm integrating from pi over 4 to x of secant squared t dt. So the integral of secant squared we know is tangent. And then if we evaluate from pi over 4 to x, what are we getting? Well, we're getting tan of x and then minus tan of pi over 4, which will be tan of x minus 1. Okay, great. So the derivative then, with respect to x of this thing, f of x, is just going to give us sort of the guts right back evaluated at x. So this would just be secant squared x. And certainly you can see that the derivative of this, the constant, will go away, and we just, crud, I keep running off the page, sorry. It's getting towards the end of the chapter. So if I take the derivative of this thing, I get back right at this thing. Let's try another one. So 87, big F of x equals the integral from -2 to x of t squared minus 2t. And we want to use the second fundamental theorem of calculus to find the derivative of this function. So f prime of x clearly then equals x squared minus 2x. You could literally just plug x into here, and there you go. Okay. It gets a little more complicated when they start putting some weird functions up in the upper limit. So f of x equals the integral from 0 to the sine of x, the square root of t dt. Okay. So you can't just say this is equal to the square root of sine of x. It won't work that way. What you have to do then is u sub. So you'll say let u equal sine x, and sort of go from there. So du with respect to x is equal to cosine x. So the derivative of big F with respect to x is going to equal the derivative of big F with respect to u times the derivative of u with respect to x. Okay, so we have a chain rule type idea going on. So we'll rewrite f of x with this substitution, okay, and it'll become f of u equals the integral from 0 to u of the square root of t times dt, and then to find the derivative of this thing, the derivative of f with respect to x. So now it's a u of x. Let me clear this out. Sorry. So what are we doing? I want to find the derivative of this thing. So the derivative of f of x with respect to x is going to be equal to the derivative of f with respect to u times the derivative of u with respect to x. And that was this statement. The derivative of f with respect to u. So I need the derivative with respect to u of f of u, which would be the integral from 0 to u of the square root of t dt, but then I have to multiply it by the derivative of u with respect to t. Okay. So by the second fundamental theorem of calculus now, you can figure that part out. This part right here is just the square root of u, so you just plug u in for t. And then this portion is coming from our u sub up here. So it'll be times the derivative of u with respect to t, which is cosine x. And then the square root of u is sine x. And then we have cosine x. Ugh. All right, so hopefully I didn't butcher that too much. But that's the idea. Okay. Now we shift our focus a little bit to physics. If we didn't already have enough going on. We have net change versus total distance traveled. Okay. Okay, so we'll call the net change displacement. And that'll equal the integral from a to b of the velocity function, which will be, the antiderivative of the velocity is the position function. So we'll have s of b, which is your finish point, minus s of a, which is your starting point. Okay. The other type of metric we'll want to know is the total distance traveled. Okay. So in that case, you're going to want to consider the absolute value of the velocity function from a to b. Okay, so what's the difference between these two? Well, consider you have a particle that goes from position 1 to maybe position 3, and then it goes from position 3 to position 2. The net change is just the difference between the ending point, and sorry, I went off the page again. So, all right, so I'm going from 1 to 3, and then from 3 to 2. My particle goes here to here, and then here to here. So the net change is the difference between the ending point and the starting point. It's just 1 unit, okay, going from here to 2. The displacement, the total distance traveled then is going to be 1, 2, 3, and then 4. Right? So this is actually 4. That's the difference between these two interesting thingamajigs. So anyways, let's look at a problem in the book, and we'll call it quits. So number 101. I have v of t equaling 5t minus 7, and we're going from 0 to 3. Okay, so first thing I want to know is the displacement. That's the easier version of this problem. I just need to do the integral of 5t minus 7 from 0 to 3. Okay, so I'll have 5t squared over 2 minus 7t from 0 to 3. So I'll have 45 halves minus 21, which is the same as 42 halves minus 0 minus 0. That'll equal 3 halves, okay, for our total displacement. Okay, then the distance traveled, you need to do the integral of the absolute value of the velocity function. So the integral of the absolute value of 5t minus 7 dt. So for absolute value problems, you need to split those up, right? So 5t minus 7, the absolute value of that thing is negative 5t plus 7 if t is less than 7/5, and then 5t minus 7 if t is greater than or equal to 7/5. Okay, so we need two integrals. First one, the integral of negative 5t plus 7 dt from 0 to 7/5, and then plus the integral from 7/5 to 3 of 5t minus 7 dt. Okay, so finding antiderivatives, I have negative 5t squared over 2 plus 7t from 0 to 7/5, and then plus the antiderivative of that, 5t squared over 2 minus 7t from 7/5 to 3. Okay. Evaluating these things, I get 49/5 minus 245/50 plus 45 halves minus 21 eventually. Okay? I'm not putting in all my information. Part of it will be 0. I've done this earlier. And this will equal 113 over 10. So sorry for skipping over the arithmetic there. I'm going insane. Okay, I need. Okay, sorry about that. We'll see you next time.